Hey guys, this is Mark Carrion. This is notes part 4, which involves equilibrium calculations. Posted the notes this morning, I believe. This is going to go through those. For those of you that can't make the Google Meets, this is the lecture for these notes. So really, watch the video, watch the videos that I've embedded within this video or in the notes on Classroom, and we'll get going here. So. Let's look at something known as the equilibrium constant. Now, this is an important concept. The equilibrium constant, as you're going to see, it's a ratio of product concentrations in moles per liter to reactant concentrations in moles per liter. So let's say we've got an equation where A is turning into B. These are just fake things. And so let's say at equilibrium, we have 2 moles of this per liter, and we have 1 mole per liter of that, of B. And so what we're saying is we're looking at the ratio of those. So if I plug it in, K equals B divided by A, which would be, in this case, we've got a 1 that would be divided by a 2. And so the K value would be 0.5 in this case. Now, that ratio is going to tell us a lot about what's going on at equilibrium. What you have to remember is that at equilibrium, both of those reactions are still going. Nothing stops at equilibrium. In fact, it's dynamic equilibrium. Things keep moving. We have A turning into B. We have B turning into A at the same time and at the same speed if it's at equilibrium. But again, it doesn't mean that at equilibrium, the concentrations of each are the same. So that's one thing to remember there. Secondly, it helps us determine whether we have more products or reactants when a reversible reaction is in equilibrium. And you could see that in my last example there. We had more B than A, or sorry, more A than B in that one. We had 2 moles of A per liter and 1 mole of B per liter. It's in equilibrium. Things are still moving, but we don't have as many products as reactants. Okay, and so the K value can really show us a lot about what's going on at equilibrium. Let's look at this example. Here we have A plus B making C plus D. Now, real quick before we go too far into this, just a heads up on what you're looking at. These are representing coefficients. So, the numbers that we usually see in front of the compounds that we're looking at, or the elements that we're looking at in an equation, these would be the coefficients in front. So they just represent that. So we can get a general idea of what the K constant equation looks like, or the expression as we call it. This is the equation that we're looking at here. And the expression is how we would actually plug it in. Like I did earlier with the 1/2. That was a really easy example of this. So when you're looking at this, you're going to notice that the products are always going to be on top because it's products to reactant concentration. So products are on the top, which are these guys, and the reactants are on the bottom, which are those guys. And you notice that the little a for whatever substance A represents is shown on here as an exponent. Okay, and that's literally what we do in this case. For B, again, that little b is shown there as an exponent. For C, the coefficient there is shown as an exponent, and the coefficient for D is shown as an exponent. So that's what we do, and we plug those in. Now, let's go back to the example that I just showed you with A going to B, and look at that again. So we have A turning into B, and you notice there's no coefficients that written in front of them, which means they're 1. So technically what I'm doing is putting B, and it's to the first power, which we don't usually write, and A to the first power. And I gave you those concentrations, and let me move that. And I gave you the concentrations as 1 mole per liter here, and 2 moles per liter there. And they're to the first power, which means they just stay the same. So it's still 1 divided by 2, and you get 0.5. The best part of the K expression and constant is there's no units because everything cancels out, and we just generally don't use units because it's a ratio. So right now, if I look at this equilibrium system of A going to B, the reactants are favored, meaning there's more reactants at equilibrium than products. So if I have a factory that's trying to make B, the way it is right now is not that great because I'm not getting a whole lot of B at equilibrium. So this is where Le Chatelier's principle comes in that we were looking at. If I want to get more B, I can add more A into there and remove the B, and I can get it to shift to the right and make more B. And so, you're gonna see that kind of stuff happening. Now, the one thing that will change the K value is temperature, and you're gonna see that in just a sec. Temperature is the only thing that can change the K value. So let's go here. These are a couple of like hints and tips you can use to help you. If that K is greater than 1, which in our example it was 0.5, it wasn't. But if it's greater than 1, you have more products at equilibrium. We say they're favored. Okay, so we have more of them, and we use the word favored. If K is less than 1, if K is less than 1, then the reactants are favored at equilibrium. So in our example, we had, again, 0.5, which is less than 1. And you notice we had more reactants at equilibrium than products. Okay, you can tell a lot about the kinetics of a system and the equilibrium of a system by this. There are no units for K. I mentioned this. Enjoy the time off from having to write units. Okay, we've been units this, units that all semester and all year, and this is your one chance not to have to do it. So do not put units. There are none. In equilibrium, we only study gases and aqueous solutions at equilibrium in these K expressions. We leave the solids and the liquids out. And here's the reason why. Some of the things you can do with Le Chatelier's to get it to shift, to control a reaction. One thing you can do is increase pressure. Well, if I have a solid shown here, those particles are already close together. No amount of squeezing on these guys is going to get them any closer. So pressure doesn't affect solids. And liquids are also equally close together. They just slip and slide past each other. So we have solid, and this is a shout out to Mr. Gibson, who used to teach at Madera South. You have solid, you have liquid, and you notice they're both close together. But what's not close together are gases. Okay, gases are all over the place. And what else is not close together are aqueous solutions. So if you have a container full of salt dissolved in water, you got a bunch of little Na pluses, ions, and chloride ions floating around, and they're separated. So you can change the concentration of this and gases, but you can't change the concentration of a solid or a pure liquid like water. You cannot change its concentration. It's moles per liter, and that's not going to change. Okay, so that's the reasoning why. Okay, for that. So real quick on concentration, and I'm posting another video, if I haven't already, from Bozeman on solutions, and we don't want to skip over solutions before we talk about this. So definitely watch that video if you struggle with this concept of moles per liter. Okay. In chemistry, we use moles per liter for concentration, and concentration really is how much stuff is packed in a certain amount of space. It's kind of like density in a way, but we're looking at moles per liter instead of grams per milliliter or grams per centimeter. So moles per liter is also written as just simply a capital M. So you don't have to write that. You can just write a capital M, and chemists know that means moles per liter. 3 moles per liter can also be said or pronounced, or whatever you want to say, spoken as 3 molar. So I've got a concentration of HCl that's 3.0 moles per liter. I'm not going to say that. I'll tell the students I've got a 3 molar concentration of HCl here. Okay. The stuff that comes for HCl is hydrochloric acid. That stuff comes from the factory for us as 12 molar on the label. And this is kind of like percent in a way, because if you think about like alcoholic beverages, which you shouldn't be thinking about right now because you're not 21 yet if you're in my class. But I guess you could think about them, but definitely don't drink them. But in wine, a lot of wines are around 12% alcohol. And that means out of that solution, 12% of it is alcohol. And, the rest of it is mostly water and some other compounds that are in there that give it the flavor and the look and the color. So 3 molar is kind of like that. It's how much stuff is in there that we're looking at. Okay. So M is molarity. That's our concentration. And how many moles are dissolved in 1 liter. Now, of the whole solution, meaning the mixture that's there. So it's not, 3 moles of HCl in 1 liter of water. It's in 3 moles of HCl in 1 liter of water plus HCl. So both those volumes are included in the 1 liter. So that's a little bit on concentration you should have a background of. In past years, we used to cover this a lot more heavily before going into this. But with some of the earth science stuff we have to do, it kind of gets left by the wayside, and we kind of just say, well, this is concentration. So it's good to know the background for that. Okay. So let's, oh, by the way, this video is really good on this. So I would say after the notes, if you're looking at this going, I'm confused, Markarian's confusing me, go to Mr. Anderson with Bozeman Chemistry, because he does an excellent job of talking about this again. So it's another source. You're going to have to learn to use your sources for AP Chem, College Chem, really any high-level class. There's a lot of info and there's a lot of resources you guys have access to. Make sure to use them. Okay. So let's look at an example of calculating the KEQ, and we're going to use probably the now sick of Haber process. For being such a jerk in real life, the guy sure gets a lot of attention in our class. And I spelled his name wrong, but you know what? It's Haber. Oh, wait, no, that's right. I'm sorry. It is Haber. You got N2 plus 3H2 yields ammonia. Okay. At equilibrium, it says a gas mixture contains 0.1 molar. Remember, that's molar. N2. 0.2 molar H2 and 0.050 molar ammonia NH3. Calculate the KEQ. Okay. So what I do on this, let me get my ugly face out of the way. Blast. Let me go back one. Sorry, guys. Okay, I'm struggling as usual. Okay. So we've got K here. And so here's what I've done. I've set up the KEQ equation. Remember, the 2 shows up here for ammonia. The 3 shows up as an exponent for hydrogen. And there's a 1 there that nobody writes, except I just did it. And nobody wrote it there either, but it's there. Okay. So then I just plug in the numbers. And so for the ammonia, it's 0.05, sorry. For the hydrogen, I plug it in there. It's 0.2. And 0.1 for the nitrogen. And then I do the math. Now you got to remember to square that number. You got to cube that number and then also multiply it by 0.10. So you want to make sure, orders of operation are used here. So in the, in the calculator, be careful with parentheses. Use them. Don't ever feel like you're overusing parentheses. It really does help make sure you get it right. So I would try entering that at home if you're watching this in a calculator, and make sure you get the 3.1. Now, here's what I can tell from this 3.1. We're talking about K, and K's out there, or you're just now learning about it. But this is what this is telling me. At this temperature that we're running this experiment at, I've got something that's greater than 1, which means the products are favored. Whatever I'm doing, pressure, temperature-wise, and everything else here, but at this temperature, I'm getting 3.1. And I'm willing to bet, these numbers would not happen in real life probably to get that K. But the K constant can be used with other values. So once you have a K constant, if you're at the same temp, you can use that K constant for any experiment because the only thing affecting K is temperature. So if these values were all different, I could still plug them in and I still should get 3.1 as long as I'm at the same temperature. Okay. Can't stress that enough. The K will not change unless you change the temperature. So all the values that you see would adjust to match up with that K value. Okay. And that's that, we keep it simple. The K doesn't change unless you change temperature. Say it with me at home. The K doesn't change unless you change temperature. Okay. And if I didn't mention it, the K does not change unless you change temperature. Okay, let's look at example 2. All right. Now I'm all over the place here, literally on the screen. Here we've got H2 hydrogen gas plus iodine as a gas in this case. Iodine's usually a solid, but we don't know what temperature we're at. And it's making 2 moles of hydrogen iodide gas. And that's also falling backwards and decomposing into those guys. So we got an equilibrium system here, got the double arrow and reversible reaction. Now, this one, they give you the moles, but they also say it's in a 1 liter flask, which means this is 1 mole per liter or 1 molar. This is 1 mole per liter or 1 molar. And then it says at equilibrium, 0.5 moles of HI, again, that's per 1 liter, are present. And it says to calculate the KEQ, okay? So here's how we go through this one. First, I figure out the molarities, which I just told you, it's 1 liter, so these are easy to calculate. If you have 1 mole in 1 liter, that's 1 molar, okay? So we've got the iodine checked off here. We've got the H2 here, and we've got the hydrogen iodide checked off there. So we have all of our amounts. So that's the first thing you want to do. And follow these steps when you're doing practices. Okay, it really helps. Okay, so we have those guys. Now it says use an ice table. Now this is where, and this is one of my favorite things in chem, because what we're basically doing is stoichiometry without the dimensional analysis in this. And this is the beauty of an ice table. And some of you are going to look at this and go, well, why didn't you do this when we were doing stoichiometry? You can. There's uses for this. But let's look at this and let me show you how this thing works. Okay. I set up a table, and we call it an ice table because each letter over here spells out ice. So we have initial concentrations, which are shown here. And these were given to us in the problem. If you go back and look at the problem again, that's what we got, okay? We're assuming that we put these 2 guys into a flask and there was none of the product in there at the start, okay? So we put in a 1 molar H2, 1 molar I2 into a sealed flask, and they start reacting, okay? They start colliding, breaking bonds, forming HI. When they got to equilibrium, which is shown with the E in ice, we ended up, it says in the problem again, that we had 0.5 molar HI. In fact, let's quickly go back to the problem so you can see that. 1 molar, when you put it in, per liter, 1 molar, 0.5 molar. And here's the key thing you got to look at when you're reading these. It says at equilibrium, we have that, okay? And that's the 0.5 moles per liter that we have there. So you got to read the question carefully, okay? Don't look at this and go, I don't understand. I don't get it. Go back through, watch this again. Really pay attention to what I'm saying about reading the question, okay? Because that's key. So again, we got all those, okay? And real quick, let me make a note on this because I think it's important. These are initial concentrations because it says they're reacted, which means I put them in there, okay? This one's at equilibrium because it said it in the problem, okay? So let's go back to the ice table here. So once I fill in the information I have, then I got to figure out the rest of it. Now, you're going to notice here I put in a plus 0.5. How do I know the change, which is the C in ice, is plus 0.5? Well, it's real easy. If I start with 0 and the question told me I got to that, then the change has to be that. Super easy. You just got to be able to add. It's 0.5 minus 0. Okay, so keep it simple. All right, so then let's look at the other changes. Okay, what I want you to keep in mind here, and this is where the stoichiometry part comes in. That's a 2, but these are both 1s. If this changed 0.5, then what do these guys have to change if the ratio is 1 to 2? Okay, that's what you need to be thinking about on the ICE table. Okay, and the answer to that is, well, half, since I've got a 2 here. Whoops. Sorry. Since I have a 2 there and a 1 there, then the change, this has to be half of that. Okay. Now, the other question is, why is it minus? Well, that's because it's got to go down to make more HI. So when you look at this, one side has to be positive and one side has to be negative. And whatever side is 0, the change has got to be positive. It's got to go up. Okay, I mean, there's no other way around it. You can't go below 0 on the HI, so it has to go up. Okay. All right, so that's where we're getting these numbers. So then if the I2 is a 1 and the H2 is a 1, then their changes are the same. And remember this, and go back and watch this again if you have to, but if they're on the same side, they both have a negative change. And since they're both 1 and 1, they have the same change. Okay, that's really stoichiometry. When we use the equation, we're using those ratios. And that's what we're doing here. So then the last thing I do is plug in, well, okay, what are they at equilibrium if they went down by minus 0.25? So 1 minus 0.25 is 0.75. And for the I2, it's going to be the same. Now, I've got the equilibrium values, and that's what we need to plug them into that K expression that we looked at earlier. So let me clean this up here. We've got everything we need in that equilibrium portion. So whatever goes in here goes into the K expression, which I plugged in down here so you can see it. And you notice all those numbers go in there. And don't forget, HI was 2 up here, so we got to square it. That's probably one of the bigger mistakes. Don't let the little easy mistakes mess you up on this. So once you get the equilibrium values, that goes in the K expression. That's what the ICE table is for. It allows us to figure out stuff we don't know from information that we do know. We knew this, that, and that. And we were able to figure out that and that from it. Okay. This is honors level stuff, but there are regular chem students across the nation that do this all the time. We reserve it for Honors Chem because they're going to go into AP where we use this a lot. Don't think of the ICE table as something to be learned. Think of the ICE table as one of your friends, okay? Like a real friend, one that actually helps you, okay? And so once I plug that stuff in, now I've got the K value. It's 0.4444, okay? It's less than 1, which means that the reactants are favored at this temperature at equilibrium. And you can see it. There's 0.75 of them, and there's only 0.5 of that. Okay, so it works out. It makes sense. And so that's how we get the K when we don't know all the equilibrium concentrations, okay, for that. And you can tell a lot from the K value. Now, this video, definitely watch it because it's some students from an Honors Chem class made this video. And if you like Vanilla Ice and the Ice Ice Baby song, I highly recommend the video, okay? I'm going to make a separate video with these CFUs and go through it with you guys, and I'll try to get it posted today as well. I'm going to post the first half of this video right now, as soon as it gets rendered, and then I'm going to do a second video that goes over these practices with you guys so you can try them out, okay? Don't give up on this. I know you're learning from home, at a distance here, but watching this, looking through the notes, search out YouTube and Google for more resources. If I'm not posting enough to help you, you got to look for the resources. Okay, you guys can do it, and you'll be fine. Okay. Talk to you soon.